Have you ever wondered how those everyday electronics take the alternating current from your wall outlet and turn it into the smooth direct current they need to operate? It is a fundamental process, and understanding its core calculation is key to circuit design. To calculate the output direct current voltage of a rectifier, you typically determine the peak voltage of the alternating current input, subtract any voltage drops across the diodes, and then consider the ripple voltage if a filter capacitor is present. The underlying principle involves converting the alternating current waveform into a pulsating direct current. Ideal diodes conduct only in one direction, effectively chopping off or inverting parts of the alternating current cycle. Real-world silicon diodes introduce a forward voltage drop, usually around 0.7 volts, which reduces the available peak voltage. This voltage drop is a crucial factor in practical calculations. Let us break this down: 4 common rectifier types. For a half-wave rectifier, the peak direct current output voltage is simply the peak alternating current input voltage minus the diode forward voltage drop. If your input is a 120-volt root mean square alternating current, its peak voltage is approximately 170 volts. Subtract 0.7 volts for a single silicon diode, giving you about 169.3 volts peak pulsating direct current. For a full-wave center-tapped rectifier, you use half of the transformer secondary's peak voltage and subtract one diode drop. So, if the peak voltage across half the secondary is, say, 24 volts, your peak output would be 23.3 volts. With a full-wave bridge rectifier, 2 diodes conduct simultaneously during each half cycle. Therefore, you subtract 2 diode forward voltage drops from the peak alternating current input voltage. For our 170-volt peak input, this would be 170 minus 1.4 volts, resulting in 168.6 volts peak pulsating direct current. After rectification, a filter capacitor is almost always used to smooth out this pulsating direct current. The average direct current voltage with a capacitor present is roughly the peak rectified voltage minus half of the peak-to-peak ripple voltage. The ripple voltage itself depends on the load current, the capacitance value, and the input frequency. A larger capacitor or lighter load results in less ripple and a direct current voltage closer to the peak. A common misconception is that the direct current output will exactly match the root mean square alternating current input. However, due to the diode drops and the nature of rectification, the peak direct current voltage is always slightly less than the peak alternating current, and the average direct current voltage with filtering is generally higher than the root mean square input voltage but lower than the peak rectified voltage. Understanding this distinction, especially the difference between peak and average voltage, is vital for proper power supply design. Overlooking the diode drops or ripple can lead to underperforming or incorrectly sized components. By systematically accounting for the peak alternating current voltage, the inevitable diode forward voltage drops, and the smoothing effect of the filter capacitor, you can accurately predict your rectifier's direct current output. This methodical approach ensures you design reliable and efficient power conversion circuits, transforming raw alternating current into the stable direct current needed for sensitive electronics.